Hey guys, let's learn about the rate equation. So we've talked about the rate of reaction, the rate of a reaction. So we need an equation now to actually determine that. Okay, and so for reaction that looks reaction that looks like this, and really you'll notice in the rate equation we're only concerned about the reactants here. So for this reaction, the rate of the reaction is going to be equal to K, something that we call the rate constant, and it's just a value that either you're going to have to be given or you're going to calculate it in the problem. It's a constant that's different for each equation. The rate is equal to the rate constant times the concentration of chemical A raised to a power that is going to be the order of the reaction with respect to this particular reactant. That's a value that I'll have to give you, times the concentration of the next reactant, which in this case is B, raised to the power of whatever the order of that, of the order of the equation with respect to that reactant is, okay? And so this is going to be actually really simple. We're just going to do some problems and plug in the value, but the whole using of the order and raising to the power, that'll make more sense once we actually do the reaction. I'm sorry, do an example. So let's just write down the rate equation here, and we'll jump directly to an example because I think that's going to be the easiest way to understand this, okay? So we'll go in our book to example 15.1 on page 459. So the problem says this: the reaction below is first order with respect to H2 and second order with respect to NO. When the concentration of H2 is 0.012 molarity and the concentration of NO is 0.045 molarity, the rate of the reaction is 3.41 molarity per second at 25 degrees Celsius. What is the rate constant and overall order for this reaction? Okay, so let's just first of all rearrange our rate equation. It's given us the rate and it's asking us for the rate constant. So if we want to find the rate constant, we just rearrange this equation and we say that rate is equal, K is equal to rate over concentration of A to the X power, concentration of B to the Y power. So that's actually the equation we're going to use, right? So let's write that down and we'll just fill in the numbers that they gave us. K is equal to the rate is 3.41 molarity per second, divided by the concentration of chemical A, which in this case is H2, and they give us that concentration as 0.012. And they tell us that this reaction is first order with respect to H2, okay? So we're going to raise it to the first power. And then the concentration of NO is 0.045 molarity. I forgot my unit there. I want to put that in there because the units are going to be imported at the end here. And it tells us that this particular reaction is second order with respect to NO. So we're going to put a power of 2 on that, okay? And so as it turns out, once we punch these numbers in our calculator, we get a final value of 140,000, all right? But we got to get our units right, and the units can be kind of tricky. All right, so our units on top are molarity per second. Our units on bottom, this is molarity raised to the first power, so it's just an M. This one is molarity raised to the second power, right? So it's going to be M squared. So our unit on top then, molarity per second with molarity cubed on the bottom. All right, and so if we rearrange that, it's basically molarity on top with S times M cubed on the bottom. So molarity, we'll put molarity first, divided by molarity cubed times S. Well, if we do that, this molarity is going to cancel out with one of these and we get squared right there. So our final unit is going to be 1 over molarity squared times S, right? So that's the unit that we have, really bizarre unit. And what we're going to see in our next problem is the unit is not always the same for every equation. It's going to depend on what these powers are right here on these X and Y values, the order, the overall order of the equation. Now they did ask us that in this problem as well. So this is one answer. That was what the rate constant was equal to. The other answer, they asked us what the overall order was. And the overall order is just the exponents on each of our concentrations right here added together. So the first one, it was 1, the second one was 2, and that equals 3. Okay, so the overall order was 3. All right, so let's do one more problem, and we will be done for today. And the second problem, so this problem says the following reaction is first order with respect to H2O2, first order with respect to I-, and 0th order with respect to H+. When the concentration of H2O2 is 0.01, so they give us the concentration of each of those guys, and then they tell us at the rate, what the rate is, and they want us to find the rate constant again. So we're going to be using this equation here, okay? So let's just write that down. K is equal to, they give us the rate to be 2.3 times 10 to the negative 6 molarity per second. Rate's going to always have that, that unit on it. And so now we got to write down the concentration of, I'm not going to rewrite that. The concentration of H2O2, they give that to us as 0.01. And they tell us that the reaction is first order with respect to H2O2, so it's raised to the first power. For I- right here, the concentration of that they give us to be 0.02 molarity. I forgot my unit again there. Molarity. Again, this one's first order, so it's raised to the first power. And then the last one, the concentration of H+ is 0.0005 molarity, and it's raised to the 0th power. So we got a 0 right there, right? And I don't know why I did the slash through the 0 there and didn't do it through these, but I did. So let's do this calculation. The first thing that we need to understand is that anything raised to the 0 power is just equal to 1, right? So that one's not even going to factor into this equation. So when we punch these numbers into our calculator right here, we get a value of 0.012. And then we just have to make sure we get our units right. So on the top, we got molarity divided by second. All of that over molarity to the first power times molarity to the first power is going to be molarity to the second power, or molarity squared. And so our overall unit then is going to be, molarity over molarity squared per second. And so this ohm's going to cancel out with one of the ohms down there for a final value of 0.012, 1 over molarity per second. So again, remember, if we think back to our last problem, the unit we got was 1 over molarity squared per second. And I just want to show you something. If you'll notice here, the overall order for this guy is 1 plus 1 plus 0, all right? That was the last one. So the overall order is 2, and the unit on M is a 1. Well, for the last problem, the overall order was 3, and the unit on molarity was 2. So the unit on the power on molarity is always going to be 1 less than whatever the overall order is. But the main thing that I just want you to remember is that the unit for rate constant depends on overall order, right? So that unit is going to vary depending on what the overall order of the equation is. Okay? That's it for today. Have a great week.
Yes, Mr. Mayor. I see. Stoichiometric crisis, you say? Having trouble balancing equations again. Yes, sir. I understand completely. I'm over.